The marine environment is home to activities which involve the use of cellular communication links for land-based and nearshore communication. Communication is very important to fishermen on land, in boats at sea, and even incoming and outgoing ships in case of any emergency. The marine environment has the following characteristics: open space with little or no obstruction, a highly reflective surface, distances that may range from line of sight to non-line of sight over the horizon, marine vessels that may be transmitting radio waves, temperature and air pressure fluctuations depending on weather systems and the time of day. The project highlights and compares 4 different propagation models for the marine environment: free space path loss, Okamura-Hata, ITUR P1546, and Longley Rice. Factors that affect such propagation include atmospheric absorption, curvature of the Earth, roughness of the sea, and climate. The 2 models that are applicable to the marine environment are Longley Rice and ITUR P1546. This is because they account for reflection, refraction, and scattering, and are specific to sea propagation. The main advantages of ITUR P1546 are that it accounts for time, location, and atmospheric refractive index variability. The advantages of Longley Rice are that it accounts for terrain, climate, subsoil conditions, and ground curvature. Link budget is a calculation that accounts for all gains as well as losses throughout the link system. This section describes how limiting factors and performance metrics were used to determine the maximum link length of the designed communication link. Recall that there are fundamental and practical limitations. Some of these performance metrics were used when determining the communication link length. A communication link between the transmitter and receiver is possible if the difference between the transmitter power and the free space path loss is greater than the receiver sensitivity. This is illustrated by equation 1, which includes the effect of antenna gains and was used to calculate the FSPL. Equation 2 is the FSPL equation, which was used to determine the link length D. Shannon's law was used to calculate the channel capacity. The bandwidth B was specified and the receiver sensitivity was used as the signal power. A value of noise power was determined based on the assumption of the noise being thermal noise. This section summarizes the calculated and simulated results. The curvature of the Earth was taken into consideration by Radio Mobile, which resulted in shorter link lengths than calculated. The difference between the uplink and downlink was due to the base station having a larger transmitter power than the mobile station. A channel capacity was calculated as shown. However, the application of emergency marine communication only requires a capacity of approximately 1 kilobit per second. Therefore, based on Shannon's theorem, a lower transmitter power could possibly be used as long as the communication link is maintained greater than 111.9 kilometers. This screenshot shows the maximum mobile station transmission distance as determined by Radio Mobile. There are some key considerations that should be accounted for when designing a communication link within the marine environment. These are receiver sensitivity, antenna gain, loss, free space path loss, and frequency. Some important quality metrics that should be accounted for are signal-to-noise ratio and bit error rate. All these factors play an important role in defining the maximum link length of a communication link and the quality of the received signal. Thank you for watching.